Imagine a world where computers could operate with virtually no energy loss, a dream that has tantalizingly eluded scientists and engineers for decades. But here's the twist. A British startup named Vaire is boldly stepping into this uncharted territory, claiming to have achieved what was once thought impossible. In an unprecedented move, Vaire has unveiled its groundbreaking Ice River test chip, showcasing a system that recovers energy using reversible computing principles. This achievement could redefine the future of computation, offering a glimmer of hope in our quest for sustainable technology. Based in London, Vaire is making waves as the first company to demonstrate adiabatic reversible computing with net energy recovery. Their inaugural test chip, Ice River, employs a resonator design fabricated in 22-nanometer CMOS technology. The results are nothing short of remarkable. Experiments conducted on-chip revealed that a capacitor array, driven by Vaire's resonator, achieved an energy recovery factor of 1.77 compared to traditional square-wave-driven circuits. For an adder circuit embedded within Ice River, the factor stood at 1.41. According to Hannah Early, Vaire's chief technology officer, any recovery factor above 1 would have been considered proof of concept, a milestone they've now surpassed. We set out with one goal for our first tape-out, to validate energy recovery through reversible logic, Early explained to EE Times. And it's finally happened. After 4 years of relentless focus as a small team, we've unlocked a new scaling law. This breakthrough could pave the way for chips capable of performing computations with negligible energy consumption, thanks to the innovative application of reversible computing principles. But here's where things get controversial. Reversible computing remains shrouded in misconceptions. Many believe it's too far-fetched or impractical, especially when considering Landauer's limit, which defines the theoretical minimum energy required for irreversible operations. Rodolfo Rossini, Vaire's CEO, argues otherwise. When people hear reversible computing, they dismiss it because we're still far from Landauer's limit, he told EE Times. However, CMOS technology itself cannot reach that limit, and you're now less than an order of magnitude away from hitting its terminal constraints. Rossini emphasizes that while CMOS isn't ideal for reversible computing, pursuing this path is essential given the explosive growth of AI workloads and the slowing pace of Moore's law. Despite the inherent challenges, such as designing complex resonators and addressing other technical hurdles, reversibility holds immense potential for delivering significant net gains. The journey of reversible computing involves layering overheads upon overheads, Rossini remarked. Yet, if executed correctly, these efficiencies can outweigh the added complexity. Vaire's story began back in 2018 when Rossini, a serial tech entrepreneur, stumbled upon reversible computing while exploring what he calls orphan technologies, innovations abandoned due to lack of need during the heyday of Moore's law. Intrigued, he connected with Mike Frank, a pioneer in the field, who introduced him to Hannah Early, then a PhD researcher specializing in unconventional computing. Together, along with Acorn/ARM veteran Andrew Sloss, they formed Vaire. As Rossini puts it, each member of our team discovered reversible computing, became fascinated, and committed fully to the cause. Reversible computing isn't a novel idea. Its roots trace back to Rolf Landauer's pioneering work in 1961. Landauer proposed that retaining information rather than erasing it during computation could conserve energy. His colleague Charles Bennett expanded on this in 1973, suggesting that computations could be reversed to reclaim energy instead of dissipating it as heat. However, implementing this concept in hardware is anything but straightforward. Efforts to create reversible logic gates gained momentum in the early 1980s with contributions from Fredkin and Toffoli, whose designs remain influential in quantum computing today. By the mid-1990s, MIT researchers developed the pendulum chip, demonstrating the viability of logically reversible architectures. Yet, coupling logical reversibility with an effective energy recovery mechanism remained elusive until Vaire took up the challenge. Early explains that achieving adiabatic switching, an essential component of reversible computing, requires maintaining thermal equilibrium to prevent energy dissipation. Even though transistors aren't burning energy during charge and discharge cycles, the energy must go somewhere, she noted. Our resonator captures this energy after each clock cycle and reuses it in subsequent cycles. One of the key innovations in Vaire's approach lies in their resonator design, which dynamically adjusts voltage levels during transitions to minimize energy loss. This requires precise waveform shaping and advanced distribution networks, presenting unique engineering challenges. While much of Ice River's development occurred semi-manually, Vaire is actively working on automating parts of the process to streamline future designs. Another critical aspect is speed. Adiabatic switching inherently involves trade-offs between operational frequency and energy savings. Ice River currently operates at 500 MHz, but Vaire aims to push this closer to 1 GHz in upcoming iterations, despite the additional complexities involved in clock distribution. As Vaire moves toward commercialization, they recognize the importance of compatibility with existing software ecosystems. No one will rewrite software from scratch to accommodate reversible computing, Rosini stated. Instead, Vaire plans to embed reversible optimization directly into hardware, ensuring seamless integration with conventional systems. This strategy allows them to accelerate existing code without requiring massive overhauls. Despite the hurdles ahead, Vaire's vision has struck a chord with potential customers eager to explore energy-efficient solutions. Chief Solutions Architect Alex Fleetwood highlighted the diverse range of applications under consideration, from AI to specialized ASIC architectures. We're opening doors to optimizations in both planar CMOS and beyond, he said. This flexibility is incredibly appealing to our partners. So, what's your take? Do you think reversible computing will revolutionize the industry, or are we still chasing an unattainable dream? Share your thoughts in the comments below.